Okay, so in our last lecture, we have seen a given system of forces, say this Fi, I1 to N, these forces, if you're taken, it can be reduced to a single force R and a couple of moment G, and this entire combined system is said to be dyname. Usually, R and G are having the same, are having different line of action. There is R line of action is different from the axis of this couple, but in it may happen that we can find out a single line of action for this both R and the axis of the couple. In that case, we say that the D name is reduced to a range. Okay, so that's what I've written here also. In general, the vectors, if you see the note, in general, the vectors and the R and G that we have just seen, okay, have different directions. If they coincide, then we say this is called a range. That is, the D name is reduced to range. Okay, so this thing that is denamed to range is supported by this theorem. What is this theorem saying? Here, you are given a system of forces acting on these particles P1, P2, Pn of a material body. This entire system is equivalent to a range consisting of the resultant force R and a couple PR acting along the straight line. This is a straight line. G minus R cross R equals to PR. That P will be proved to be this one, or combining of this moment of G and the line of action of R, resultant R. Okay. So let us see how we can do this. Okay. So we have already we know about the name. We are just trying to go or and understand to the range part. Okay. So what was given to us? We suppose what we initially provided with a system of forces, as I said. Okay. So if your force system of forces, if I1 to N has been reduced to R and G. So let us now talk about this system. Okay, we won't go back now, right now to this Fi again. Okay. So let us consider this R was acting along OA. Okay. So let me just put it more straightforward. Your line of action of R might be this one, anything. Whatever is your line of action, you consider here as a base point of. Okay. And then let the couple whose axis is obviously passing through O as per our theory we have seen, this be the couple. This be the couple axis, OB. Okay. So this is OA, okay, and this is OB. Okay, and let me this be the angle between the two. Okay, so I have also listed it down here. OAR's direction, OB axis of the couple, angle of AOB equals to theta. What we do now, is this one thing before I go into this thing, let you just have this idea that this couple can be resolved into two component couples. How? I considered R as one direction, OA as one direction, and another line perpendicular to this OA, this OC. So that means as if this OA and OC is acting as a set of mutually perpendicular axes. So this G can now be resolved into two directions, along this one, along this one. And theta be the angle, what will be the component of G along this one, G cos theta, and component along this one will be G sin theta. So that's what I have written it out here also. I am drawing OC perpendicular to OA in the plane AOB. Okay. And that means what? This plane AOB means this is the plane. Okay. And you are dropping a perpendicular OC onto the plane. Okay. Now your G was acting along OB. So if you now just, as I said, we will resolve it. This one will be one axis like this. And this one will another. Okay. So I am getting my couple decomposed into two perpendicular lines. Okay. As I have written here. Okay. Axis. Now you see the second couple acts in the plane AOD. Second couple means this G sin theta. Okay. Acts in the plane AOD and can be replaced by two unlike but equal, that means equal magnitude parallel forces G cosine theta each. That means what I'm saying of here, this is your G sin theta. Let me write here. This is your G sin theta couple, moment of the couple, one of the components of this original couple. Okay. Now it is acting along this axis that is revolving like this. So this axis is again perpendicular, this AO plane, AOB plane. Okay. So what can I say? This can be now replaced by two parallel but opposite in direction, that is anti-parallel, I should say, and equal in magnitude forces in the plane AOD. Okay. So That's why I've just giving this picture here. If you see in this figure, this one, from here to here, if you just come. So this is the perpendicular to this plane, this entire plane here you can see. So this plane AOD is also coming here. Okay. Now I am trying to replace this couple via two forces. So what can I do? I can bring two forces, this one O1A1 and another I consider along this OA dash, just opposite to the direction of OA. Okay. And this O1 is to be taken in such a way that you get the couple, moment of the couple as G sin theta. That means what I am doing, I am taking one force like this, another force parallel to this, anti-parallel to this of equal magnitude. That means if it is a force R I am taking, then it also will be the force R, but at a distance opposite to the direction of R, because it is you are taking like this, then I am taking like this one, but at a distance O1, such that the moment of these two forces, moment of the couple formed by these two forces is equals to G sin theta. So I need to just adjust this, I need to just adjust this O1 distance. Okay. So here you get this thing. Here you see what I am doing for this replacement. R along O A dash I am taking. And R along O1A1 I am taking through the any other point, this one on OD, that is in the plane AOD, because your couple was acting the plane AOD, such that, as I said, this distance adjustment thing, R into O1, R is the magnitude resultant, because the two forces you are taking are of magnitude R into the distance, that is the distance between the two component forces of the couple, must be equal to what? The moment of the couple should be G sin theta. So this should be equal to G sin theta. That means this was our unknown thing which we were adjusting after we have set, or here I have considered this R as one of the component forces of the couple and this one as another component of the forces of the couple. Then I need to adjust only the distance. This is how I am adjusting the distance. O1 should be placed because O is already fixed as the base point. So I need to place this O1 suitably. Okay. So I am getting the idea where to place this O1. Okay. Now you see, as soon as I do this thing, what is the advantage I am getting by my choice here? See, I have taken R along OA dash, and there was already R in the original thing we started with, OA along OA. So these two forces are cancelling each other because they are passing to the same point, they are of the same magnitude but opposite direction. Okay. So you are cancelling actually this effect and this effect. So what you are left over with? You are left over with this force. Okay. And remember that you were also having, once you have decomposed this couple, original couple, into G cos theta and G sin theta. G sin theta I have replaced somehow here. G cos theta is already remaining along this with OA as the axis. Now you see this OA is the axis of G cos theta couple. Okay. So G cos theta now can be replaced again by the equivalence principle. It can be replaced. The axis can be shifted parallel in the same plane. In the same plane means the plane of AOD. Okay. It can be shifted. So I am shifting it from here to here. The axis I can shift as per the equivalence principle. I am shifting it here. So what you are having now, you are having a force along O1A1. You are having a couple whose axis is along O1. So this O1A1 is the single line of action of the resultant R and the axis of the couple, which is remaining over this G cos theta. Okay. So you are ultimately having this one. See here I have written O1A1 parallel to OA, I have shifted it. So finally we are having a single system S dash. That means we started with the system say S0. If I were the forces given, we initially shifted over to S dash where we had R and G, but their line of action of R and axis of couple G were different. This is for the dyname part. And from there we moved on to the range. Here we are getting a single line of action for the force R and the couple of moment G cos theta. So here is better if I write G cos theta because we are left over with this amount of couple after all this component breaking and everything. So G cos theta. Okay. So the entire system of forces, as I have written it out ultimately, is consisting of R along OA couple and a couple in moment G and OB is now reduced to system S dash. Okay. So it was the dyname part. This was the dyname part. And this has now become, this S dash has now become the range. Okay. And line of action of this one, the common line of action which we were in search of is the coincide with the axis of the couple. Line of the force and the axis of the couple, which couple G cos theta is the O1A1 common line of action. Okay. So this O1A1 common line of action has a special name. It is said to be the Poinsot central axis. Okay. Now the combined system, that is the dname up to the range which we have got, is usually denoted by gamma. That's written here. Gamma denote combination of R along O1A1 and the couple moment G cos theta with axis O1. So same thing. Gamma is known as the range, okay, in which the original system of non-coplanar forces acting on a rigid body is reduced. This already we have seen. Okay. Now let us see, or rather find out the moment vector of the couple, G cos theta. Moment vector of the couple we need to find out. Now what we have here in our hand. If we are considering only the couple part, moment vector of the couple, this is the axis of the couple after shifting, right? So what is the direction of the axis of the couple? The direction of O1A1. Now what is the direction of O1A1? Nothing but the direction of the resultant. Now how do you get the direction of any vector? R by mod R, unit vector. So this is the direction. And what is the magnitude of the couple? G cos theta. So the moment vector of the couple, which we are left with, is G cos theta, is the magnitude, and the vector is given by R by mod R. So this is the thing I will now down here. See, this moment vector of the couple, this one, equals to G cos theta magnitude and the direction. Now you just can manipulate it here just by multiplying above and below by this magnitude of R, so that you are left over with R square here in the denominator. Okay. Let me enlarge it a bit. R square here in the denominator. Okay. Now this one, if you see carefully, this is nothing but G dot R. And you are left over with this singular here. So I am saying that this I have ticked already. G cos theta and this R together gives you this quantity G dot R. R square remaining below, and this direction R remains as good. So this entire quantity G dot R by mod R square is said to be the pitch of the range. Okay. So the range ultimately is nothing but R comma PR. R is the force part, that is the resultant part, and PR from the couple part. Okay, so this is the range actually. So if you want to find out or say what is the range, this is the actual range. Okay, the expression. Now from here also you can see alternatively from here in terms of gamma, if I want to express, okay, moment vector of a couple, the same thing, G dot R by R square R. Okay, then G dot R, you can just simplify, or you just alternative writing, you may say. This one, you are just segregating. Just simple, you can follow it on your own. So this is your gamma by mod R and times, this is actually the magnitude, and this remains the vector. Let me rub it out. This remains the vector. Okay. So this gamma here, G dot R by mod R, is said to be the Poinsot's moment. So if you consider, or rather compare the pitch of the range with the Poinsot moment, you are getting P equal to gamma by mod R. Now one thing is important. You see here, the dimension of R is this one because it is a force, ml1 t to the minus 2. Then dimension of gamma also you can easily calculate from here, and you can just check if this gamma is becoming this one. Dimension of gamma is becoming this one. So ultimately the pitch of the range, this is actually important. The pitch of the range is having the dimension of the length here. Okay. So G dot R by mod R is giving you, ultimately if you put back all these dimensions here from gamma, I have just simplified it. It is becoming L mn1 t to the power minus 2. That is L square mn m to the minus 2. That's what I am putting here. and below is mod r, so mlt t to the power minus 2, l to the power 1 t to the minus 2. So here you cancel out and you are left over with one dimension of the length. So that's what I have written here. Okay. So each of the range is actually having the dimension of length. Okay. Now, once we have reduced the range, our next question will be, he was saying the line of action of the resultant and the axis, the couple are coincident now in the range. So what is this equation of the line of action? That means what is the equation of the Poinsot central axis? Okay. So this is the thing range we have proved. Now to find out the line of equation of the line of action of the range, equation of the line of action of the range. Okay. So what for that, what we need to do? As we do usually, any line whose equation you are trying to find out, to take any point over it, any point position. Okay. And then you try to frame an equation involving this R, obviously involving the conditions given. Okay. Then that will be giving you the locus of the any points movement on that line. That means you will be getting the equation of the line. Okay. So what do? I start with that usual strategy. Let P be any point on O1, A1, such that PV, the position vector of P, is equals to R. So OP equals to R. Okay. OP is equals to R, this one. So this is the thing you just see. We have already done this thing. Anything, this was the resultant given, this was the couple, then we have decomposed it, then somehow we have managed to shift this entire couple into G cos theta and then shift the axis of the couple here along O1, A1. So this O1, A1 is now our concerned line, P, C, A, Poinsot central axis. So what I am doing, I am taking any point P, okay, on this Poinsot central axis, whose position vector is R. This is R, okay, OP. Okay. Now you see, you started with the system of n forces, n three-dimensional forces I started with, okay, which was first reduced to dyname. That means the resultant and a couple, okay. So now what we are trying to do, we are trying to find out the moment of the system of forces with respect to O. This is our strategy. Okay, because we are trying to find out the line of action of O1A1, that is the line of action of the Poinsot central axis. We are starting how? We are taking the moments, this one. We are taking the moments of all the forces about O. Now you see, all the forces, moment when I am trying to calculate with respect to O, but our O is the best point, and as per we have taken, this OA is the line of action of R, that is the resultant of all the forces. So if I want to find out the moment of all the forces about O, that means that is equal to the moment of resultant about O. But the resultant itself is passing through O. So the moment of the resultant will be 0. So what we are left over with? The moment of the couple. Because you just see, we have in our dyname two parts, R and G, in dyname part. This is not having any moment about O, because as per our design, we are taking O as the best point. We started with like that. Okay. So R will not have any moment. So who will have moment about O? G. That the couple will have moment. So G is equals to sum of moment of all these forces Fi about O. Okay. That means moment of the range about O. Because these are all equivalent system. I am saying repeatedly, dname up to range. You have just reduced it, but you are actually dealing with the same system. You started with this Fi system is 0. This is S0. Then you have gone to dname part, dname, where you had R and G. Then again by further reduction, you have gone to S dash, the range part, which has got RPR. So R, let me write below, RPR, R, comma, PR. This one you are having. Okay. So moment of this one equal to moment of this one equal to moment of this. I am trying to find the moment of this one with respect to, that means I'll be finding on moment of this system with respect to O. But here the moment of R will vanish. We will get only the moment of G. Whatever we get, that will be again equal to the moment of the range with respect to O. That's what I have written here, equal to 1 after number steps. That is the moment of the range about O. Now range consists of R acting through O1A1, this one, O1A1, and moment of the couple. Now, what is the moment of the couple? We already write PR. Just now I have shown, which is PR, this thing. The gamma is the moment of the vector couple, gamma. this one, you see, moment of the vector couple gamma, what did I find out? PR. So moment of this couple is equals to PR. So I should add this to up, add what to up? Add moment of R acting through O1A1 plus moment of PR of the couple. Now what is the moment of this R acting through O1A1? This R is acting through O1A1 like this, here, like this, and you have taken any point P on it. So what is the distance? How do we calculate the moment of any force? R, that means any point of application of the force here. P is the point of application of force R cross with respect to O, you are measuring the distance. OP, actually this is OP cross the magnitude, that is the force itself, that is R. Okay. So OP cross R. Now what is OP? OP is nothing but R. So R cross R. So this is what I have used here. So G is equals to R cross R plus PR. This was we are supposed to prove, that we have proved. Huh? And using this, see what we are trying to do. Once we had actually twofold motivations. One, to find out the expression of G which we said before in the theorem. See here I have just listed it out. You recall back. Here. See, that will be the this one. Force and this acting along the straight line. This is a straight line. And this G, P already we have obtained. And now we will be, this is the line of action. So as I said, involving R, I will be forming an equation. So here I am getting an equation. Okay. So this one is giving us the equation. G is equals to R cross capital R plus PR. Okay. Now, if you put all this in the Cartesian coordinate system, what is G? G is the couple's moment. Now, if I write as an element, then G equals to element, R equals to the resultant components. If you just put X, Y, Z, then you can just simply find out this one. Nothing to say here. Now, once you find out like this one, you can easily see. So what do? You just equate, because these two are the same. So once you equate it, you are getting what? This as the line of the action of the force resultant and the couple's axis. That means the equation of the points of central axis. Okay. So in terms of the Cartesian coordinates, you can put like this. Now from here only we can find out the invariants. So what are the invariants? The quantities which will never change irrespective of the choice of the base point. So whatever base point you take, the quantities will always remain the same. So what are these invariants in our case? This is the resultant R and the pitch of the range. These two will never vary. So for what? To prove that, what we do, we consider another base point and find out again this quantity R, resultant's magnitude, and P, and see whether they indeed remain the same or they change. Okay. So I consider another base point, right? Given system of forces was this thing. It reduces to a resultant R and a couple G with respect to the R dash, I consider now, and couple G dash, actually it will be here. I have missed it. It will be couple G dashed with respect to the base point O dash. Okay. So the initial system was this. If you recall back when we did the theorem, we considered this one was R and this was the base point and this one is a G. Now I am considering another system. F reduced to this system we have done. I'm now considering F is reduced, Fi, the system is reduced to another system. But suppose this base point has now moved to this. This is the base point, not this one. And this remains your R dash and G dash. This remains as your R dash and G dash. Okay. So now I want to find out it is resultant magnitude and the pitch of the range will remain the same. Okay. So whatever might be the R dash, it should be the summation, vector sum of all these components of all these forces. So it should be equal to this one. I have already missed this direction signs. You have to be careful about it. Okay. But this is again equal to what? R. Okay. So R dash equals to R, already you have got. So if you now take out the resultant, obviously that will be the same. So first invariance proved. Then G dash. What is G dash? G dash is the couple moment. Okay. So how can you find it out? Just by summing up the moments of all the forces. So Fi are the forces. But what has changed? The position vectors of the points of applications have changed. So now if you consider this figure here, see here from here, this one was as axis. This one was original system, say P1, one force I'm considering. This was say R. Now what I have done, I have shifted my O to some other point O dash, and this point is now having this R dash, R1 dash as a new position vector. So once you have that, I am considering this triangle O P1 O dash like this. O P1 P1 and O dash. Let me draw it this side. It's not getting like this. O, so this is the O dash and this is your point P1. So this is your R1, this is your R1 dash, and this is O dash. Okay. So like this. So from here only I can find out here, as I've seen here also, from this triangle what you are getting, any, I have to consider P1, you can consider P2 for any of this P1, P2, P and this will go be true. So R dash plus R1 I dash equals to Ri from here by triangle law of vector addition. Okay. So once you get this, Ri dash is clear. Ri minus R dash. Okay. So once you get this thing, you can easily put it or insert it here because you need it here, right? This Ri dash was there in G dash expression. So if I put it here, what I'm supposed to get? Just this thing. Now you simplify it. Okay. So what you are left over with is Ri cross Fi is G itself and minus R dash cross R. This because this Fi is nothing but R. Okay. So G dash is nothing but G minus R dash cross R. Okay. Now you see if this is your G dash, then G dash dot R dash you have to find out because you have to find out or rather prove if P is invariant. Now P is G dot R by R square. Now you see, I have shown कि R resultant magnitude, R itself, resultant itself is equals to R equals to R dash. I have proved it. So the resultant magnitude will remain the same. That is the denominator won't cause any problem. It remains invariant. So we need to prove the invariance of the numerator part, right? So I started with, that means I need to show ultimately G dot R equals to G dash dot R. This magnitude. Okay. So I started with this one. So I started with this one. Just now I have computed the expression of G dash that I am using here. Then if you take the dot product of this thing with dot R dash, this thing, what do you get? This one minus this thing. But again, you see this is a box product containing this R dash and R are the same. So you are handling a box product containing two identical vectors. So that means that should definitely vanish. That would give you a scalar 0. So it will go to 0. So what you are left over with? G dot R. So you see our original intention is satisfied. We have obtained this. We have to G dash dot R dash equals to G dot. So it remains invariant. This is how we have proved it. So let us stop it here.